Hey everyone. Application of trig functions. Before we start on some of our applications, let's do some startup or a little bit of review, some warm up on um, the key characteristics of these sinusoidal functions and how they behave. Okay, this will help us a lot when we do some problem solving. All right, recall. Characteristics of special transformations. So phase shift between sine and cosine functions. So down here, this is that's y equals sine of x, and this is y equals cosine of x. All right, so here's our two starting points. Let's recall. To express the function y equals sine of x in terms of the cosine function, you must transform y equals cosine of x with a phase shift to the, well, let's take a look at this. How do I make the cosine, how do I make a cosine function the same as y equals sine of x? Well, I have to phase shift it by that distance. What is that distance? That is 0 to pi over 2. So we phase shift to the right by pi, by 1/4 of the period. So this will be important later. By 1/4 of the period. The c value, well, when we look at this, right, the period of our cosine function, so if I do this right here, that's 2 pi, folks. Okay? The period of our sine function is 2 pi. Okay? So 1/4 of that period, so 1/4 of 2 pi is equal to pi over 2. And so the c value is positive pi over 2. Okay, so remember this 1/4 of the period. Okay, this will come in handy later. So y equals sine of x is equivalent to y equals cosine of x minus pi over 2. So we are shifting the cosine function by a c value of pi over 2, which is pi over 2 units to the right, or pi over 2 radians to the right, and that makes the cosine graph this equivalent statement. We can rewrite the sine function in terms of cosine with a phase shift of pi over 2. Let's look at it another way. To express the function y equals cosine of x in terms of the sine function, you must transform y equals sine of x with a phase shift to the, well, let's take a look at this. If I start here, this is my sine function. I want to make it look like, I want to make this graph the same as cosine, but I want to rewrite it in terms of sine. What sort of phase shift do I need? So here's cosine. I need to go this way. This is to the left, and this is by pi over 2 radians. So to express the function y equals cosine of x in terms of the sine function, you must transform y equals sine of x with a phase shift to the left by 1/4 of the period. Again, for this same reason here. Okay, 1/4 of the period, which happens to be pi over 2, but since it's to the left, the c value is negative pi over 2. Okay, so y equals cosine of x is equivalent to y equals sine of x minus negative pi, or plus pi over 2. Okay, remember that. Next part, recall characteristics of special transformations, a phase shift between sinusoidal function and the reflections. So let's take a look. When the function y equals sine of x is reflected in the x-axis, so a equals negative 1, the resulting function is y equals negative sine of x. So we know that. So the graph we are talking about here this red function is y equals sine of x, and when we have an a value equals -1, well, we reflect it, so this is y equals negative sine of x. Okay, negative sine of x. All right. When the function y equals negative sine of x is transformed with a phase shift left or right, let me write this neatly, sorry folks, left or right by how much of the period? So we know the period is 2 pi, either the cosine or sine. Okay, so how far are we shifting it? So if I start here and I go here, this is exactly pi units. So I can go this way, or I can go this way. Same distance, pi units. So it's exactly left or right by 1/2 of the period. So 2 pi times 1/2 equals pi units. Okay, so the resulting function is equivalent to the original function y equals sine of x. So let's summarize. Y equals sine of x is equivalent to y equals negative sine of x plus or minus half of the period, which is pi. Okay, let's do it for cosine. When the function y equals cosine of x is reflected in the x-axis, a equals -1. The resulting function is y equals negative cosine of x. So here is y equals cosine of x, and here is in dotted y equals negative cosine of x. When the function y equals cosine of x is transformed with a phase shift, again, we'll see left or right, so you have options, by 1/2 of the period for the same reason. So if I start here, this is on cosine, and I go, let me do this one. If I start here, I can go to the right. Well, what is that? This is 180 degrees, or pi radians. I can go to the left. Well, what is this distance? This is 180 degrees, or pi radians. Okay, so exactly half of the period. The resulting function is equivalent to the original function y equals cosine of x. So y equals cosine of x is equivalent to y equals negative cosine of x plus or minus pi radians. Okay, so there we go. This will be handy when we do the next page, when we're just going to, I'm going to show you a graph. Then I'm going to ask you to write the equation of the function in 4 different ways. Okay, so these 2 little tips here with the reflection of the sinusoidal function and then just the phase shift going from sine to cosine, this will be very handy in the next part. All right, let's try these 3 practice problems before we hit our applications. I do have to mention from the previous page, we went over these wonderful relationships. If you need help visualizing these, go back into your notes and hit these QR codes or these links, and just go to Desmos. These are Desmos links, right? So Desmos. Hit these links and revisit all of these relationships. Super, super helpful. Okay, same thing here. Okay, you can see the phase shifts happening in real time, which is super helpful. Okay, so let's go back here. I'm gonna go to this page. Here we are. All right, number 1, folks. All right, more graph reading. This is I would say probably the hardest part about trigonometry so far is I give you a graph that's obviously of a different shape, and then I ask you, well, give me an equation. So remember those rules or those relationships for the special transformations we did yesterday, and let's apply it to today, because we're going to write 4 different equations. Okay, so this is where the challenge is. First, let's go through some basics. So what is the amplitude? Well, the amplitude is, well, I see that d equals 0. I don't have a vertical shift. So that's my sinusoidal axis, so d equals 0. Well, if d equals 0, well, this is my min, which is -3. This is my max, which is +3. So the amplitude, that's just 3. You can do min minus, max minus min divided by 2. You can do that equation. That's 6 divided by 2. That equals 3. So my amplitude, or my A value, is 3. What about period? Period, let's pick 2 points here. So I'm going to do this, folks. Let's say this is A, and let's say this is not A. Let's say this is B. Okay? When I highlight this from A to B, that is a half a period. Okay? So A to B is half of 1 period. Okay? What is that distance? So this is 0 right here. This is at 0. Well, where do we end up here? This is each tick mark, that's pi over 6. This is 2 pi over 6. This is 3 pi over 6 right here. So we're going from 0 to 3 pi over 6. So my half period is equal to pi over 2. Okay? So if a half period is pi over 2, then my full period is pi over 2 times 2 equals pi. All right, so my period is pi. What's my b value? Well, b value, 2 pi over absolute value of b equals pi. Okay, and then that means b equals 2. Okay, so I got my a, b, and d values. Now let's add in a phase shift. Okay, so we got to look at this graph and think about phase shift. So I'm going to draw a couple more points here. Let me use a different color. Okay, when I talk about phase shift, I'm going to assume minimum phase shift. Okay, so let's assume minimum phase shift. And I need to read this graph to see where I sit with a phase shift. First with A is greater than 0. Okay, folks, let's do this first one here. Y equals A sine of B, X minus C plus D, where A is greater than 0. So we have our A, B, and D values. We need to find our C value. So I'm going to plot point E here. Okay. And I'm going to plot point D right here. Okay, so E and D. Okay. So from E to D, I'm thinking about the sine function that does this, right? So I'm thinking about the sine function. If I start from point E, okay, imagine it doing this, right? I need to shift this back this way. So that way. What is that? Right? So if I think of that, right? The easy way to think about it without trying to look at all those tick marks is this way. So point E would start here, right? At 0, and then that is exactly what? That is a quarter of your cycle. So that'd be pi over 4. So from E to D, that is pi over 4. radians. Which way? To the left, right? So we need to go to the left. Imagine a sine function shifting to the left there. Okay, so that means a c value of negative pi over 4. And so what does that do for us here? Y equals 3 sine of 2 times x minus pi over 4, minus negative pi over 4, or plus pi over 4. Okay, and then the d value is 0, so there is no d value. Okay, second one. What happens when a is less than 0? Well, we get a reflection, right? So I'm going to create this point F right here. Okay, I'm going to ignore, well, let's leave point E there. So I'm going to create this point F, and then let me sketch in the reflection of the sine function to illustrate what happens. Okay, so there's in dotted line. Oops. Okay, there we go. So from F to D, how far is that? Highlighter. F to D. Well, we can either read the tick marks or take a look at it. That's exactly a half cycle. Half cycle, folks, or half a period, is pi over 2. So let's go to pi over 2. That's pi over 2. And which way are we going? We're going shifting to the left from F to D. So pi over 2 radians left. Okay, so that's a c value of negative pi over 2. But remember, for a reflection, I can also go to the right. I can go this way. I can shift to the right, and I'd still match. I can still match. What if I go this way? So if this entire graph shifts this way, I can still match the function. So I can say or pi over 2, positive pi over 2. So my new equation becomes y equals, now I'm going to throw that negative in there, right? Because a is less than 0, negative 3 sine of 2 times x plus pi over 4 minus negative pi over 2. That's my transformation. Okay, so off to the side, pi over 4 plus pi over 2. That equals pi over 4 plus 2 pi over 4. That's 3 pi over 4. Okay, so all of this, I'm going to clean this up. This is plus 3 pi over 4. Okay, what about the other way? So y equals negative 3 sine of 2 x plus pi over 4. So I'm taking this original equation. I adjusted it for the a is less than 0 right there. Okay, and then I'm applying my phase shift. Let's do the positive phase shift. That's plus pi over 2. Well, off to the side, pi over 4 plus pi over 2 equals pi over 4 plus 2 pi over 4. That's, hang on folks, sorry. This is, if I'm applying this one, it should be minus pi over 2. Sorry about that, folks. Minus pi over 2. So this becomes minus pi over 2. So that's a minus minus. That would be negative pi over 4. Okay, so all of this becomes minus pi over 4. If you sit there and graph this, you'll see that these two are equivalent. Let's go back. Let's not forget about this shortcut. So if I go back here, right here, folks, remember this, all of this. When I take a sine function and I reflect it, well, this is the relationship that it is a phase shift left to right. by exactly 1/2 of the period. So if I go back, my period here, folks, is pi. 1/2 of that is pi over 2. Well, there's my plus or minus pi over 2, the phase shift. So that's the shortcut. You can use that shortcut and then get these two equations. Okay, so that is the sine ones. Let's go over the cosine ones. Okay, let's do it a couple ways. We'll use our relationship between sine and cosine after. Let's do the graph reading first. So I'm going to clean this up a little bit, folks. Let's start over. Okay. Okay. Cosine. Let's write this sine function in terms of cosine. So we need to apply that phase shift that's going to get us there. Okay, so interesting. So if I start here, let's call that point A. We know our cosine starts right on the y-axis right on the y-axis at its maximum, right? So in this case, no phase shift is necessary. No phase shift. So C equals 0, folks. That's nice and easy. Okay. So y equals, the A, B, and D values are all the same. Y equals 3 cosine of 2x. Well, there's no phase shift. There's no vertical shift. So it's just y equals 3 cosine of 2x. Okay. The other way to think about it, folks, is this. So I'm going to move this up. Let's go back to what we talked about in the previous page. This part. Okay. So let me just highlight it here. To express cosine of x in terms of the sine function, you must transform the sine function with a phase shift left by 1/4 of the period. Okay, 1/4 of the period, right? Because we showed graphically why it's 1/4 of the period right here. Okay, so let's go back. Let's see if that's the case. So 1/4 of the period, and that's to the right. All right, let's just make sure. That would be taking the sine function and when we convert the cosine, quarter of the period, so 1/4 of the period. So let's take a look at that. 1/4. Let's think about this. Here's the period. 1/4 of the period is pi over 4. Okay, and so if we need to adjust that by pi over 4, so to express the function y equals sine of x, so I should start here. Y equals sine of x in terms of the cosine. That's what we're doing, not this part. This is the other way. To express the function y equals sine of x in terms of the cosine function, you must transform the cosine function with a phase shift to the right by 1/4. So that's positive pi over 2 in this case, but 1/4 of the period we saw here is pi over 4. So I need to go to the right or add positive, or we need to go to the right by pi over 4 radians. So if I do that here, right, this is what I'm doing, folks. This part here, when I rewrite it, y equals 3 in terms of cosine of 2 times x plus pi over 4. And then I need to shift it by pi over 4 to the right, which is minus pi over 4. That all becomes just this. Okay, and then we end up with the same thing. Okay, last one here. Y equals a cosine of b times x minus c plus d. Now we're going to reflect the cosine function, and then what is that phase shift that is necessary? So I'm going to do this. So I have point A, and I'm going to draw point B prime here, B prime, and then let me draw in the reflected cosine function here. Okay, so when I do that, I need to go this way. Okay, but you know from reflecting, we can go, either go this way to the left, or I can pick this point and go to the right, right? So there's two ways we can do it. So B prime to A, that is, well, graph reading, B prime to A, if I'm shifting that far, right, I am doing this. So that's a half cycle, right? So that's pi over 2. So B prime to A, that's a pi over 2 radians to the left. So what is my C value? C equals negative pi over 2. Negative pi over 2. Okay. And then so what happens? So y equals, now my A value is negative, cosine of 2 times x, okay, minus negative pi over 2. And then that is just plus pi over 2. The other way we can think about it is, remember, or plus pi over 2, right? Because of the same relationship, when you reflect it, it's a horizontal phase shift in either direction, left or right, by the same number of units, or thinking about it as pi over 2, or half of your period. So that y equals negative 3 cosine of 2 times x minus pi over 2. And that's the other way you can think about it. Okay? Hey everyone, I'm going to look at number 1, the startup, and number 2. So let me do number 1, where we came up with a graph of y equals 3 sine of 2, and that's x minus c, theta minus c, which is plus pi over 4 plus pi divided by 4, and then our d value is 0. Okay, that's what it looks like. So let me zoom in here. Okay, that's a maximum at 3, 0, 3, and 3 pi over 6, so pi over 2 minimum right there. So the points we remember are here. Okay, that's that, and then this is the other point that we remember right here. Okay, that was what we saw in our graph here, right? Yep, pi over 2. Okay. right, so that's our sinusoidal function. And then we want to see when we create equivalent. So I'm going to copy this, folks. And let me go down here. I'm going to start a new one. Let's bring this up. Okay. We said when we make the negative of it, so the negative, what happens, right? We know that if we take the original graph, right, there it is in green. So if I turn it off, there's in red, there's in green overlaid. If I make a less than 0 right there, well, now it's out of phase by what? By 1/2 of the period, right? The period is pi. So now if I label this point right there, right? So this point and this point, the two maximums, once I made, I'll do that again for effect here, so right there, and once I make it negative, right, so it's a reflection of the red graph, okay, now we are out of phase by pi over 2, which is 1/2 of the period. That's what we said when the a value goes less than 0, so the a value becomes negative from 3 to -3. We're out of phase by pi over 2. So to get the green graph, okay, to get the green graph to match the red graph, I can either go plus pi over 2, or minus pi over 2 phase shift. So watch what happens here. So I'm going to go, oops. So on the green graph, right, plus pi, oops, no, right here. Okay, on the green graph, so right there, plus, let's add pi over 2, and then we are matched, right? Remember, it's like saying minus negative pi over 2. That's a shift left, right? Because the c value is negative, right? So there's one way. The other way is if I add pi over 2, a positive pi over 2 c value. So divided by 2, and there it is. The two graphs match. Okay, so that's one way to think about it. When we evaluate this, folks, pi over 4 minus pi over 2 is just minus pi over 4. So let's fix that. Minus pi over 4, and then the two graphs match. Okay? The other way to think about it is with a cosine value. So I'll leave these two on. When I hit the cosine value here, let's match everything. We know it's just a phase shift, so it's 3 is the a value, 2 is the b value, the d value is 0. Okay, so right now, okay, right now, that's 2. So right now, with a d value of 0 and a c value of 0, the functions match, right? So if I turn off the blue, turn off the green, turn off the red, here's my cosine value when I plug in everything with a c value of 0, d value of 0. When I turn on the red, there it is. Here's the green. That's the one we did with the -3 sine value. And then now the cosine value. So what that means is that I don't need a vertical shift, so that's 0. And I don't need a horizontal phase shift. So there we go. So so there's the original, there's the sine, here's the third version with the cosine. Okay, so I'll leave that in blue. All right, the last one is when I create the negative of the cosine function. Let's see what happens here. Let's put it there. and then I'm going to bring this up right there. Okay, so when I create the negative of it, well, it's going to put it out of phase by half of the period, right? Which is 1/2 times pi is pi over 2. Okay, so how do I adjust this? I can either go left or right by pi over 2. So let's go ahead and write into the red one. If I add pi divided by 2, so it's like this, minus negative pi divided by 2. And you can see the functions line up. Okay, or I can simply add pi over 2, which is that. I can subtract pi over 2. So a c value of negative pi over 2 or a c value of positive pi over 2 gives me the same result. In the example I did in class, I said it was a negative value, so I can simplify it by saying plus pi over 2. Okay, so there it is. So if I do the red, that's the latest one. I had to shift it, phase shift it by pi over 2 to the left, or you can do it to the right. There's the original, and you can see that all the graphs line up. Okay, so there's 1, 2, 3, and then the fourth one. Okay. Okay, number 2. Let's take a look at this graph, and let's figure out all our transformation parameters here. Okay. Amplitude. Well, I'm going to look at my max and min values. First, where's our sinusoidal axis? So okay, it looks like our 1, 2, 3, 4. I'm just going to count 1 from the max to the min. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's got to be at 5. So our sinusoidal axis is at d equals hang on. 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm going to count 5 from either the max or the min. So let's start here. 1, 2, 3, 4, 5. So my sinusoidal axis is right here. All right, there we go. This is d equals -4. So that's a quick one. D equals -4. All right. The max is 1. The min is -9. So my amplitude would be you can either say 1 minus -9 divided by 2. That's 10 divided by 2 equals 5. Or you can count 1, 2, 3, 4, 5 units to the sinusoidal axis. So A equals 5. Okay, the period. Let's start from a convenient point here. Let's see. Where can we start? I'm going to start, let's start right there. That's at pi over 3. And let's go half a period. And then let's just multiply by 2. So half a period. This is easy to read. That's 2 pi over 3. So 2 pi over 3 minus pi over 3. Half a period is pi over 3. And then pi over 3 times 2. That's 2 pi over 3. So my period is 2 pi over 3. Okay? So my period is 2 pi over 3. 2 pi over 3. What's my b value? So if I do 2 pi over 3 equals 2 pi over absolute value b, well, my b value has to be 3. Okay, so we got the a, b, and the d value. Let's think about phase shift for the 4 different versions of our equation. So I'm going to start off by doing this. Let me clean this up. Okay. I'm going to leave in my sinusoidal axis. Okay, let's label a couple of points. So phase shift, let's do this one. Okay, so for the sine version of this equation where a is greater than 0, let's plot 2 points. I'm going to say this is a because the sine function starts on, the way I look at it is the reference point for the sine function is that it starts on the sinusoidal axis, right? So I'm going to label this as point A. Okay, and then I need to go to point B, which is my transform graph. Well, what is that? Horizontal phase shift. Well, from A to B, that is, if this is pi over 3, this is pi over 6. So that's pi over 6 radians to the left. So C must equal negative pi over 6. So what's my equation? Y equals, my A value is 5, sine, my B value is 3, 5 sine of 3 times x minus negative pi over 6, and then our d value is minus 4. Okay, and then this part I'm going to simplify it as x plus pi over 6, x plus pi over 6 minus 4. Okay? All right, this one, let's do the next one where now a is less than 0. So the version of this function with sine where a is less than 0, what kind of phase shift do I have to apply? So let me label this as point, let me do this in a different color. This is point C. Let me label this as point C. And then let me sketch out the reflection here. Okay. So from A to C, A to C. So now we're going from A to C. Well, what is this phase shift? Well, that's just pi over 6 again, but this time to the right. So pi over 6 right. And that means the C value is positive pi over 6. Okay, so now my equation becomes y equals, my a values become negative. Sine, the b value is still the same, 3. X, instead of going left by pi over 6, I'm going to go right by pi over 6, so that's minus pi over 6. And then the d value is still minus 4. Okay? Okay, so the cosine function. So let's write this transform function in terms of cosine. If I put a dot right here, this point, we know a cosine function starts at the y-axis with a maximum. So there it is, right? So this one requires no phase shift. Okay, so that's a quick one, no phase shift. Okay, so no phase shift. So what does our equation look like? With no phase shift, that's y equals negative y equals 5 cosine of 3 times x, no phase shift, that means c is 0, and then minus 4. Okay? Folks, the other way we can think about it, and we're going to use these relationships. Wow, this is getting really, really messy. Okay. To express the function of sine in terms of cosine, right? We must go right by a quarter period, right? And we showed that relationship here, right? So I'm going to go back. Let's think about a quarter period right. What does that mean? So the period here is 2/3, right? What's a quarter of that? So let me just write it here. 2/3 is my period times 1/4. That's 2 pi over 12. 2 pi over 12, and that is pi over 6. And I need to go to the right, as we showed, right? Whenever we write a sine function in terms of cosine, we go quarter of the period, and we go to the right. So if I go to the right, I will write it as y equals, and now that it's a cosine function, 3. Remember originally I had this pi x plus pi over 6. If I go to the right, now I'm going minus pi over 6 and then minus 4. Well, this is just 0, and then we end up having the exact same equation. So this is the other way to think about it using our 1/4 relationship. Okay? All right. Let me do the last one here this time, the reflection. All right. This one right here, okay? Where now I have a reflection of this cosine function, okay? What phase shift do I need? So let me do this. I'm going to, let's see. Let me first clean this up, okay? I'm going to clean this up. Okay, I'm going to label point, let's go and point D prime right here. Okay, that's D prime. And I'm going to label point E, which is right here, point E. Okay, from here, I'm going to draw in the reflected version of the function I'm trying to get to. Okay. So from D prime to E, what is that distance? So this one right here. And what direction? Okay, what is that distance? That is pi over 3 units. So pi over 3, and which way? I'm going left. Okay, so pi over 3 units left. That's a C value of negative pi over 3. Remember, we can also go to the right. So, or positive pi over 3. So what does this look like? Y equals negative 5, so the a value is less than 0, negative 5 cosine of 3 times x minus negative pi over 3 minus 4. Okay? When I simplify that, that's just x plus pi over 3, so let me rewrite that as x plus pi over 3 minus 4. Or if I shift it to the right by pi over 3, that's negative 5 cosine of 3 times x minus pi over 3 minus 4. Okay, so two different ways to do it. You could have also thought about when you are shifting when you are shifting from the cosine function to the negative of the cosine function, so you're doing a reflection, right? Remember the relationship is half of the period for the shift, left or right. So what does that equal? Half of 2 pi over 3, and that's 2 pi over 6, or pi over 3, left or right. Okay? So if I take this equation, y equals, and I make it negative, cosine of 3, I go pi over 3 left or right, so that's x minus negative pi over 3 minus 4, or I go to the right, negative 5 cosine of 3, x minus pi over 3 minus 4, which is exactly what we have right here for our two equations. Okay? Hey, on to number 2. So we came up with this graph, so I'm going to type this in here. That is 5 sine of my b value is 3 theta minus pi over 6, so that's theta plus pi over 6, and then my d value was minus 4. Okay, so that's my sine function. Let me adjust that. Okay, so that is what we got, folks. Let me adjust the x-axis here. I'm gonna go from negative pi to positive pi, just for a bit more scale here. Okay, there we go. Hopefully that, yep, there we go. That looks more like the problem in class. Okay. All right, so that's what we did with graph reading, this graph right here in red. Okay. When we create the version of this graph, so the same graph, but we're going to make the a value negative, so negative right there. So it puts it out of phase by 1/2 of the period. So it puts it out of phase by, so the period in this case was 2/3 pi. 1/2 of that is 2/6 pi, or just pi over 3. So it puts it out of phase by pi over 3. So let me mark that point. Okay, let's label it. Okay, and then let me mark this point. And let's label that. So you can see clearly there's the right graph, the original one we graphed. When I make the a value negative, the orange graph is going to shift half of the period of the original graph, which is pi over 3. Okay? So, how do I get these two graphs to line up? Well, I need to do a phase shift. Well, what kind of phase shift do I need to do? Okay, I need to do a phase shift either by pi over 6. Sorry, I need to do a phase shift pi over 3 to the right or pi over 3 to the left. So that's like this. Oops. So we started here. If I go pi over 3 to the right, that's adding pi over 3. So I'm going to go, you have to do minus pi divided by 3. And that lines it up. Or if I go to the left, I have to add pi over 3. And you can see that that shifts it to the left. Okay? And then whichever way you do it, if I go to the right by pi over 3, I think that's what I did the class example. If I do it like that, well, that is just minus pi over 6, right? When I do this subtraction here. So let me clean that up. Minus pi over 6. Okay, and then the two graphs line up. Right, so that's my phase shift. For the second one, when we do cosine, folks, okay, let me turn on the cosine here. The A value is 5, we're not changing that. The B value is 3, we're not changing that. D value is minus 4. Okay, right away we can see that it's already in phase, right? So there's no shift to be done, and that's what we recognize right away when we make the cosine version of this, that if we plug in a C value of 0, it doesn't change anything. So that is our cosine function. Okay, so when I do the cosine function, last part, I'm going to make the A value negative. Okay, so let's bring this up. Okay, yeah, in purple. Okay, so when I make this negative, it's going to put it out of phase by how much? By pi over 3 again, right? Because you can see the maximum here and the maximum here, they're both out of phase, right? So this one and this one out of phase by pi over 3. So what do I need to do? I need to I think in the notes I said it's a shift left by pi over 3. So negative pi divided by 3. Okay, and once I do that, you can see the two graphs line up. Okay, so again, if I say plus pi over 3, that's a shift, horizontal phase shift pi over 3 units to the left. We end up getting the same graph. Hey everyone, number 3. Determine an equation of the sine curve with a maximum point at 90 degrees 4 and its nearest minimum point at 90 degrees 4 and its nearest maximum to the right at 120 degrees and 10. So first of all, without graphing, I can determine a lot of these transformation parameters. So A equals, well, first of all, the max is at a y value of 10. The minimum is at a y value of 4. Okay, so my A value is max minus min divided by 2. So A equals 10 minus 4 divided by 2. And that equals 6 divided by 2 is 3. So A is equal to 3. All right. What about my D value? D value, we can think of it as halfway between 4 and 10, or just use the equation. So I have max equals D plus the absolute value of A. Okay, max value is 10. D value, what I'm solving for, plus the absolute value of 3. So D equals 7. Okay, so that's my D value. Let's look at B value. Okay, so if at 90 degrees 4 to 120 degrees 10, from 90 to 120, when I go from a min to a max, okay, I know that is half a period. Min to the max, this would be half period. Okay, so if 30 degrees is half a period, what is a full period? 30 times 2 equals 60 degrees is a full period. Okay, so 60 degrees is full period. If the period is 60 degrees, remember this equation, period 360 degrees divided by absolute value b, that is 60 degrees equals 360 divided by absolute value b, and therefore b must equal 6. Okay, so that's our b value. Let me put a box around that. Okay, the c value. This is probably the hardest part, but not too hard. So I'm going to think of it this way. So let's graph this. One, two, three, 4, 5, 6, 7, 8, 9, 10. And then 30, 60, 90, 120, 150, 180. Okay, and then we said 94. So 94, so right there. Okay, and then 120/10 is our maximum. So 120/10. 120/10. Okay, so our max and mins occur in 30-degree increments. So I can do this, folks. So I'm going to do this. So at 30-degree increments, 4. We need to move that down to 4. Sorry about that, folks. So this one down to 4. Okay. Okay, so if I graph this, this is what it's going to look like. Okay. How do I know my horizontal phase shift? So if I start here, let me graph 4, 5, 6, 7. This is my d value equals 7. This is my sinusoidal axis, right? So if I start in, let's pick purple here, this is my sine function without a phase shift because I'm starting here right at the sinusoidal axis. I'm looking at, let me zoom in here. I'm looking at this particular part, folks. So zoomed way in. From this part here, let's just take this little arm. How do I make it look like this? Well, I need to phase shift it this way. And what is that phase shift? Okay, and that phase shift is going to be 15 degrees, right? So it's a little hard to see here, and I actually should draw this more accurately, this part right here. It should be a little tighter, this curve like this, okay? So that when I look at this phase shift from here to line it up, that's half of that 30 degrees. So that's 15 degrees to the left. So I need to phase shift 15 degrees left. Okay, so let me zoom back out. So what does this mean? That means C equals negative 15. Okay, I have my A, B, C, and D values. Okay, let me just take stock of it here. A equals 3. B equals 6. C equals negative 15. And D equals 7. So when I put it into my equation, y equals A sine of B x minus C plus D. I get y equals a value of 3. Sine B is 6. X minus 15 is x plus 15. X minus negative 15 is x plus 15. And then plus D, which is plus 7. Okay, folks, this is number 3. Determine the equation of the sine curve with a minimum point at 90 degrees and 4 and its nearest maximum to the right at 120 degrees and 10. So let me work backwards here. So the equation we started with was y equals 3 sine of 6 theta plus 15 and plus 7. I need to adjust my settings here. This is going to be in degrees. Let's go from negative 30 to 360, and then a low of 0, a high of 12. Okay, there is our graph. Okay, let me go, oops, no, that's fine. I'm going to go in negative 30. Okay, all right, so if I compare this to the sine graph without the phase shift, so let me plug this in here, 6 and 7. Okay, so here is the sine graph without the phase shift. I'm going to put in the sinusoidal axis right there. Okay, and there's my sinusoidal axis. Okay, all right. So what do I need to do to the blue graph? Okay, what do I need to do to the blue graph to make it match the red graph? The red graph is what we're looking for. Okay, so it should be 30 degrees. Okay, so the red graph, let me turn off the blue graph. We said there was a minimum point at 94. Okay, so there's 94. I'm going to label that. And a maximum point to the right at 120 and 10. So I'm going to label that. Okay, so we know those two exist, right? So if if I go back to the sine graph here, that's like asking this blue graph, how do I make it go match the red graph? So if I plot this maximum up here, that's 1510. So let me plot that point. How do I make 1510 match the red graph? Well, I have to go to the left by 15 degrees. So if I go to the left by 15 degrees, let me use my slider to show that. Okay, so I go to the left by 15 degrees. Well, what happens? Going left, 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 left. The slider is exactly at 15. And I've gone from 1510 to 010, which is my match. So if I start here, folks, I need to subtract minus, this is our transformation, negative 15 degrees. So I'm going 15 degrees to the left, or the C value is negative 15. Okay?